with security in the picture. This is what we had before. We saw how the attacker very easily was able to steal and tamper with the data. So now we're going to turn on security, and we're going to security is going to allow us to stop this attacker from stealing or tampering with that data. Now, before we do that, before I launch the applications that are going to be used in the Connect security plugins and or security extensions, and also MedCrypt's Guardian, let me show you what, if you were developing this system on your own, you could be doing self-signing with OpenSSL. And Eric, would you like to make any comments on this?
Yeah. So again, as we can see with the script, self-signed certificates can be used to enable cryptography on the device. So what's the problem there, right? This cryptography is there. We're encrypting, we're signing, we're using keys. What's the problem here? Um, yes, crypto is active. However, the devices don't know if they can actually trust one another, with who's connecting to them and who's sending data. So the data is encrypted and authenticated cryptographically, but a bad actor can still connect and exfiltrate data or send bad data to the devices to make them misbehave. So again, this is about trust. We need proper trust of the cryptographic assets as provided by the Guardian platform. But obviously, a script like this will actually turn on the security.
That's right. So I'm going to go ahead, and because, Eric has explained the dangers or the potential safety risks of self-signing, I'm going to go ahead and launch Guardian so that it can sign and provision all of the applications with the right files. Eric, would you like to make any comments on what Guardian is doing here in the background?
Yeah, thank you. I think this diagram is good. So what we're looking at here is a high-level overview of what the process looks like to provision a medical device with proper security using the MedCrypt Guardian platform. The Guardian library will generate and secure the proper key material and CSRs based on a signed security profile. Um, this is sort of the first step you're looking at here. Guardian will then send the CSRs and the device metadata via mutual TLS connection to the device provisioning workflow system, what we call the Guardian Cloud. Um, or the CSRs and the metadata can be uploaded manually or proxied in the case of an offline provisioning case, like some devices are not actually connected to the internet. They may be isolated at the hospital or on site. Um, the CSRs will be verified and processed by the provisioning workflow system. And if approved, the device certificates will be signed by keys that are stored in FIPS compliant HSMs. Then those certificates, as well as the signed security configuration that drives the Guardian library, will be transferred back to the device. And then the device has all the assets it needs to enable cryptography with properly trusted keys. So Guardian drives this crypto ecosystem, and it gets it right. So medical device engineers don't have to be experts in cryptography, and they can focus on implementing clinical features in their devices.
Thanks, Eric. And we can see here, as part of my file system now that Guardian has provided, let's just check that it finished. Yes, Guardian finished doing all the steps that Eric mentioned for all the applications in the system. We can see here how we had the different files that make up the uh, different documents that connects security extensions need in order to enable that security. We have here, for example, a governance file, a permissions file, and we can see here how, for example, the permissions file for the ARM wasn't signed before. And after running Guardian, we can scroll up here, we can see that signed permissions file with the right signature. This was provided directly by Guardian, downloaded from the cloud. And also we can see as well the private key of the ARM and also the identity, the public key of the ARM. So now what we're going to do is to go ahead and we're going to launch again the applications. In this case, they're just going to be using security instead of not using security. So let me go ahead and do that here. we go. I'm going to simply see. I'm going to pull them up here. We have the arm. It is moving. We have the patient monitor, the orchestrator right there. And as you can see, the behavior of the applications is the exact same. We are still communicating. Things are working fine. There's no impact to any of the communication streams, or the behavior apparently is the same. So now what I'm going to show you is on Wireshark. Before, if you remember, I showed the vitals topic was sent in plain text, and therefore anybody could see it. This is what I was showing before. So I'm going to scroll down here on Wireshark. And as you can see here, we don't see the topic names anymore. Now, the only thing that we're seeing is a bunch of packets that just say secure body, secure postfix, and we don't really have any information about what that is. If I open now the same portion of the packet that I showed you earlier, we can see how we have a secure prefix, a secure postfix. This is the header and the footer of the encrypted content of the packet. And if I open up this secure body and the secure payload, now I just see a bunch of encrypted bytes, and I really can't tell whether this is for the vitals topic, this was for the ARM controller topic. I don't know what this is for, but most importantly, I cannot see the actual content. If this was to be the vitals topic, I cannot see the patient's name or see anything that's going on in the system. And this is very important. Now we have encryption. Now, based on this, I'm going to go ahead and launch the attacker, the exact same application that the attacker was using before. We're going to go ahead and launch it now. I'm going to open it up right here. Again, launching the attacker application, and I'm going to try now and steal the patient's data. Let's do that. Steal, there you go. And as you can see, after a few seconds, the attacker doesn't receive that data. And it is telling us here that it tried to steal data, but I didn't receive anything because no publishers matched. It wasn't able to match any of the publishers that were sending that data. Now, if I try to tamper, remember earlier, the red graph here went up. That was the elbow, one of the joints of the robotic arm, suddenly was moving because the attacker was telling it to do so. But if I try to tamper now, we can see how nothing happened. The attacker is now saying that it tried to publish several tampering commands. It actually did, but didn't go anywhere because the subscribers are not listening to the information that the attacker is sending. So we can see how the system is fully protected now. If I try to tamper again, nothing happens. Also, very importantly, we're not only protecting the system from this potential attack, but also the system, thanks to the Connect Security extensions, and of course, using cybersecurity now, all of the applications are able to send through the login topic, through the security login topic, a piece of information telling whoever is interested in as part of this secure communication that they actually denied the attacker from joining the communication. And this is actually printed in the orchestrator. We have decided to print it here. You can see how it says that the orchestrator, the arm, the patient monitor, the arm controller, and the patient sensor, they're all reporting the same thing. And that security topic actually says this domain participant, the orchestrator or the arm, is reporting that an authenticated remote participant with this global unique identifier has been denied. So this is access control in action, because the attacker couldn't be authenticated by the rest of the applications. They're basically sending you a message saying, we have denied entry to the system to this domain participant, just in case anybody's interested. And this could be important in the future for the records of a potential cybersecurity attack. Would you like to mention anything here, Eric or Rom?
Yeah. So again, all of these devices, have cryptography and they can encrypt, sign, and authenticate data. Um, Really, the important piece here is that these are not self-signed certificates. These are not certificates generated in a way where we can't establish trust of the keys and certificates, because an attacker really could generate keys and certificates and use OpenSSL in conjunction with this whole solution, and it potentially still tamper and exfiltrate data because they can run cryptography too. The important thing is that we're establishing a trust boundary around the pieces of the device that should be communicating, and that really isolates the attacker. So without a solution where you're generating a proper root of trust and proper trust for the cryptographic assets with a solution like Guardian, you can still exfiltrate data even with cryptography active or tamper with the device.